What comes to your mind when you hear the word radioactive? Well, for me, it was this: danger, right? But in this video, we're going to try to understand what exactly is radioactive, or what does it mean, and why is it so dangerous? And how can the same thing be also useful to us? That's what we'll explore. So let's begin. To explore what radioactivity is, let's start with something that we're familiar with: chemical processes, chemical reactions. Now, you don't have to worry about this specific chemical reaction, but the thing to focus on is that in every chemical reaction, you find that the number of elements on the right-hand side is exactly the same as the number of elements on the left. For example, you have 4 oxygen atoms on the left, you find 4 oxygen atoms on the right. You have 1 carbon atoms on the right, you have 1 carbon atom on the left. This means that you will never be able to get new elements in your products. The elements on the product side will always be the same as the elements on the reactant side. But in contrast, in radioactive processes, you get new elements. What? How? You see, in chemical reactions, the reason you don't get new elements is because it's all about electrons going from one atom to another. And now if you take something like, say, carbon, and you remove an electron from it, or you add electron from it or to it, or you share electrons, whatever you do, carbon stays carbon. Electrons do not define the identity of an element. So now that brings us to the question, then what does? What makes carbon carbon? What makes oxygen oxygen? Well, to answer that question, we need to dig deeper. Literally. If you were to look inside, say, a carbon atom, you'd probably find electrons zooming around. But if you zoom in to the center, you would get the nucleus of the carbon. And you probably already know the nucleus of an atom contains protons, which are positively charged particles, and neutrons, which are neutral particles. Now, guess what? Turns out the identity of an element is defined by the number of protons. So, for example, anything that has 6 protons is carbon. Carbon is carbon because it has 6 protons. Similarly, anything that has 7 protons would be nitrogen, and so on and so forth. It's the number of protons that decide the identity. But you may ask, well, what about the number of neutrons? The number of neutrons don't matter actually. So for example, you can have carbon which has 6 neutrons, or you can have carbon which has 8 neutrons. You have different nuclei of carbon available. And by the way, such nuclei which have the same number of protons, which mean the same elements, but different number of neutrons, we give them a name, we call them isotopes. And so in order to be able to differentiate them, we have a notation. So the notation we use for representing nuclei is we write the C, and then we write the number of protons over here down. And then on the top left, we write the total number of particles, not the number of neutrons. So it's 6 plus 6, 12. So this is how we represent this nucleus. Similarly, how would you represent this nucleus? Well, we'll represent it as C, 6. It has to be 6. If it wasn't 6, it wouldn't be carbon. And then on the top left, you would write 6 plus 8. We would represent this as 14. So we would call this the carbon-12 isotope. And we would call this the carbon-14 isotope. And so you can see it's this number, the total number of particles that differentiate the isotopes. We give a name to that number. We call it the mass number. Because that number represents the mass in the sense, here you have 14 particles. So this nucleus will have more mass compared to this nucleus, which has only 12 particles, right? And so when it comes to nuclei, the mass number matters because you care about both protons and neutrons. But when it comes to chemical reactions, you don't care about the number of neutrons. You only talk about carbon because they both have the same chemical properties, but not the same nuclear properties. Now you might say, Mahesh, all of this is great, but what exactly is radioactivity and how does it create new elements and why is it so dangerous? Well, in short, it turns out that certain nuclei can be very unstable. And for such cases, for such nuclei, we just spontaneously spit out some particles, and in doing so, the number of protons in them changes. As a result, the element changes, and that's how you get new elements. That process is what we call radioactivity. Now, I know there's a lot to unpack, and we'll do this now. So the first question you might have is, what do you mean by nucleus being unstable? Now, it's not really straightforward to understand the stability of a nucleus, but to gain some intuition, think about very heavy nuclei. If you have a very heavy nucleus, you can kind of understand that it has a lot of protons and all the protons want to go away from each other because they have all positive charges. That makes it so hard to keep the nucleus together. So you can kind of see that very heavy nuclei tend to be unstable.
But what is not so intuitive is that light nuclei can also be unstable. For example, C14 is an unstable nucleus, versus C12 is stable. Now you may be wondering, well, how can that be? They both have the same number of protons. Well, turns out that stability also depends upon the ratio of the number of protons and the number of neutrons. Certain ratios are more stable compared to the others. And like I said, it's not very straightforward, it's not very intuitive, and so we'll not have to remember which nuclei are stable or which nuclei are not. But the bottom line is there are certain nuclei that are unstable. They can be heavy or they can be light. Now let's see what happens to these unstable nuclei. So let's take an example. If you take carbon-14, turns out that because it's unstable, it spits out something called the beta particle, and in the result changes to nitrogen-14. Now I know you might be having a lot of questions, like how does that happen? What exactly is a beta particle? And how did the number of protons increase from 6 to 7? How did that happen? We'll get into all of this in the future videos. In fact, this is called the beta decay. That's something called as alpha decay and gamma decay, but we'll get into all the fun stuff later on. But the point to see over here is look at what happened. We started with an unstable parent nucleus. That's what we call them, the parent nucleus, which is unstable. It spontaneously, meaning without us having to do anything to it, it just happened all by itself because it's unstable, spontaneously changed into a more stable nucleus, which we call the daughter nucleus, okay? And in doing so, what has it done? It has spit out some high energy particle. In fact, that's how you become stable, right? Like you let go of some, you release some energy. And guess what? It's this high energy particle that's what makes radioactivity so dangerous. Now you might say, Mahesh, what do you mean by high energy? Like a moving ping pong ball would literally have billions of more joules energy, right? So what do you mean by high energy? Well, you're right, but unlike a ping pong ball, these particles can actually enter into your cells, atoms, and knock off electrons, destroying bonds, which could damage the cells, which could mutate your DNA. That's what makes them so dangerous. So when I say high energy particles, what we mean over here is these are ionizing particles. We call them ionizing radiation. Ionizing means they have the ability to knock off electrons. But here's the thing. The same thing can be useful for us. For example, we can target these at cancer cells and try and destroy them. That's what radiation therapy is all about. So if we understand radioactivity, we can control it and we can use it for some amazing applications. Anyways, that's it for this video. So in short, what is radioactivity or what is radioactive decay? It's a process in which you have an unstable nucleus that spontaneously changes to a new, more stable nucleus, and in doing so, it releases high energy ionizing radiation.